Right back to it then. Another deep dive for you, still on GCSE chemistry. This time, we're looking at the numbers side of things, the quantitative stuff. You've been getting into how we measure and understand those amounts in reactions, and we're going to nail those ideas down.
Okay, yeah. Like imagine making a cuppa. You need just the right amount of tea, the water, maybe some sugar to make it perfect.
Right.
Chemistry is similar, really. We're talking the right amounts of reactants to get the products we're after. Today is all about getting to grips with the key principles of these, well, chemical recipes.
Okay, so let's jump in with something pretty fundamental. The law of conservation of mass. Could you break this down for us?
Right, so the big idea is that in any reaction, no atoms actually disappear or appear. They just kind of rearrange
So you
themselves.
look like a set of Lego, right?
Yeah, exactly. You can build different things, but you've always got the same number of bricks.
Makes sense. So nothing just pops out of nowhere or vanishes.
Exactly.
Yeah.
What does this tell us, then, about what we start with and end with in a reaction? Well, the total mass of everything at the start, the reactants, will always be exactly the same as the total mass at the end, the products.
Mm-hmm.
That's true for every single chemical reaction.
And this is where those balanced chemical equations come in, aren't they?
They do, yeah. A balanced equation is key because it shows that same number of each type of atom on both sides.
So it's not just letters and numbers, it actually means something.
Absolutely, like a perfect balance sheet for atoms. 5 carbons on one side, you need 5 on the other side, too.
Got to keep things balanced. Okay. Now, we've also got this thing called relative formula mass.
Mr.
Yeah. What is that all about?
Basically, it's the mass of a molecule compared to the mass of a carbon-12 atom. You just add up the relative atomic masses of all the atoms. So for water, HEO, hydrogen's relative atomic mass is 1, oxygen's is 16.
Right.
So the mixture of water is 2 by 1 plus 16, giving us 18.
So we just look up those atomic masses and add them up. Simple. How does Mr. link back to the equations in this law of conservation we talked about?
Well, the fascinating thing is, in a balanced equation, the sum of all the Mr. values for the reactants, making sure to multiply by those balancing numbers, it'll always equal the sum of the Mr. values for the products, with the balancing numbers again, of course. And this reinforces the idea that mass isn't just appearing or vanishing, just being rearranged.
Okay, so those big numbers in front of the formulas, the coefficients, they're really important then. Now, sometimes it looks like mass changes in a reaction, especially if gases are involved. What's going on there?
This is a tricky one, often catches people out. If you see an apparent change in mass, the key thing to think about is whether a gas is involved, either as a reactant or a product. If a gas is produced and floats off, you can't weigh it at the end, so it might seem like you've lost mass.
Makes sense.
Or if a gas reacts with a solid, like magnesium, burning an oxygen to form magnesium oxide, the solid product will be heavier because the oxygen's mass has been added in.
It's not that mass is disappearing, it's just that we're not weighing it all. Right, let's move on to this mole thing. Sounds a bit mysterious.
Not really, just a specific way chemists count particles in a substance, like atoms, molecules, or ions.
Really?
The unit is called a mole, symbol mole. Think of it like a dozen eggs, but way, way bigger.
So it's like a way of counting really tiny things. How does it relate to the mass of a substance, though?
1 mole of any substance has a mass, in grams, that's the same number as its relative formula mass.
So the Mr. we talked about.
Exactly. So for water, the Mr is 18, meaning 1 mole weighs 18 grams.
That's handy. So the Mr. tells you the mass of 1 mole in grams. What about that massive number, Avogadro's constant?
That's a fundamental number telling you exactly how many particles there are in 1 mole. It's approximately 6.02 by 10^10 emis. That's 602 sextillion.
Wow, atoms must be unbelievably tiny.
They are, and this allows us to relate that tiny world to grams, which we can measure.
Okay, so how do we actually use moles in calculations?
Well, there's a crucial relationship between mass, moles, and something called molar mass. Molar mass is like Mr. Ma, but with units of grams per mole.
Got it.
The formula is mass equals moles times molar mass.
Simple enough.
You can rearrange that to get moles equals mass divided by molar mass if you need to find the number of moles.
Could you run through a quick example?
Sure. Let's say we have 117 grams of sodium chloride, NaCl, which is just table salt. Sodium's relative atomic mass is 23. Chlorine's is 35.5, giving a Mr. for NaCl of 58.5. That means the molar mass is 58.5 geomole. To find out how many moles we have, we do 117 grams divided by 58.5 grams per mole. which gives us 2 moles exactly.
So moles are a way to count those huge numbers of particles using their mass and this molar mass thing, which comes from the mister. Now, how do we use moles in balanced chemical equations?
This is where it gets powerful. Those numbers in front of the formulas in a balanced equation, they don't just tell you the ratio of atoms or molecules, they tell you the ratio of moles too.
So if we've got, say, 2 Mg plus OO going to 2 MgO, what's that telling us in terms of moles?
It means that 2 moles of magnesium react with 1 mole of oxygen to produce 2 moles of magnesium oxide. So those coefficients give us the mole ratios directly.
So if I know how many moles of one thing I've got, I can use the equation to figure out how much of everything else is involved.
Absolutely. Like a recipe, if it says 2 eggs for every cup of flour, and you have 4 eggs, you know you need 2 cups of flour, the mole ratios work the same way.
Makes it much clearer. What happens, though, if we don't have exactly the right amounts of everything? Like, we've got too much of one thing.
That's where limiting reactants come in. In reactions, especially when mixing stuff together, it's normal for one reactant to be completely used up before the others.
Right.
We say the others are in excess.
And the one that gets used up, that's the limiting reactor.
Exactly. It limits how much product you can make. The reaction can't go any further once that reactant is gone, even if there's other stuff left over.
It's like if I'm making cheese on toast, and I have loads of bread but only 4 slices of cheese, the cheese limits how many I can make, right?
That's the perfect analogy. Identifying the limiting reactant is key because it determines the maximum amount of product you can get.
Okay, that makes sense. We often work with solutions where something's dissolved in a liquid. How do we measure the amount of the dissolved stuff, the solute?
We use concentration, which tells us how much solute is in a given volume. One way is mass per volume, usually grams per cubic decimeter, GDMR.
So if I have a solution that's 20 GDM, that means there's 20 grams of the solute in every liter of solution.
Precisely. And knowing the concentration and volume, you can work out the mass of the solute with mass equals concentration times volume. But remember, volume has to be in cubic decimeters or liters.
So if I have half a liter, 0.5 diameter of a 10 GDM solution, I've got 5 grams of solute. Now, when we actually do reactions, we calculate a theoretical yield, right? The maximum product we should get.
Yes.
But we don't always get that much in reality. What causes that?
You're right. We use percentage yield to compare the actual amount we get in the lab, the actual yield, to the theoretical yield. That's actual yield divided by theoretical yield times 100.
Okay. Why is our actual yield often lower?
Several reasons. Some reactions are reversible, meaning they don't fully convert to products.
Right.
Also, some product might be lost when separating it out, sticking to equipment or whatever.
Right.
And sometimes other unwanted reactions happen, forming byproducts we didn't account for.
So a lower yield doesn't always mean we messed up. It could just be the nature of the reaction or difficult separation. How do we actually calculate that theoretical yield, though?
There are a few steps. You start with the mass of your limiting reactant and convert that to moles, using moles equals mass divided by molar mass. Then, using the balanced equation, you figure out how many moles of product you should get from that. Finally, you convert those moles back to mass, using mass equals moles times molar mass.
So mass to moles of limiting reactant. Use the equation to find moles of product and then back to mass of product.
Got it. We also talked about atom economy. What's that all about?
Atom economy measures how many of the atoms in the reactants end up in the product you want. It's like how efficient the reaction is at using its atoms.
So a higher atom economy is a good thing. Less waste. Exactly. It's important for sustainability and cost.
Makes sense. So when chemists are choosing a method to make a chemical, what factors do they weigh up?
A whole bunch. Atom economy is one, yeah.
Yeah.
Also the percentage yield, the reaction rate, whether it's reversible and where the equilibrium lies. They also consider whether any byproducts are useful or just waste. It's a bit of a balancing act.
It's not just about making the most, it's about efficiency, cost, and the environment, too. Now, we also saw there's another way to measure the concentration of solutions.
Right. We can use moles per cubic decimeter, moldem. This is handy when we're dealing with mole ratios in reactions that happen in solution.
So if a solution is 0.5 moldamen, there's half a mole of solute per liter.
Yeah. And just like with mass concentration, we have the relationship. Moles equals concentration times volume.
And this helps when we have reacting solutions.
If you've got two solutions reacting completely, and you know the volumes and the concentration of one, you can work out the concentration of the other. First, you get the moles of the known reactant. Then, using the balanced equation, you figure out the moles of the other reactant involved. Finally, knowing those moles and the volume, you get its concentration with. Concentration equals moles divided by volume. Just remember, the volume's got to be in cubic decimeters.
Right, so the balanced equation helps link things together, even in solutions. Our last stop is gas volumes. Seems different to solids and solutions.
It is a bit different. The key thing with gases is equal moles of any gas will have the same volume, as long as the temperature and pressure are the same. This makes things much simpler.
We came across RTP, room temperature and pressure. What's so special about that?
At RTP, which is usually 20 degrees Celsius and 1 atmosphere pressure, 1 mole of any gas takes up 24 cubic decimeters. That's a really handy conversion factor.
So if I know the moles of gas, I can easily find the volume it'll occupy at RTP.
Yeah, volume equals moles times 24. So if we make 0.25 moles of oxygen at RTP, its volume would be 0.25 times 24, which is 6 cubic decimeters.
Pretty straightforward. And we can do it the other way around too, right? Volume to moles.
Exactly. And for reactions involving gases, you can use the mole ratios to find out how many moles of gas you make from a certain amount of reactant. Then use that 24 dnamol to find the volume at RTP.
So that wraps up our deep dive into the quantitative side of GCSE chemistry. We've covered conservation of mass, the mole, balanced equations, yields, atom economy, the whole lot.
Hopefully it's all a bit clearer now how these concepts connect and why they matter.
Yeah, and it's amazing to think how these calculations actually apply to real-world stuff, like making new medicines or designing greener processes. Makes you wonder how chemists use these ideas to make things better, more sustainable.
It really does.
Thanks for joining us.
Pleasure.
And we'll see you next time for another deep dive.
See you then.